5.6 Examples. This lesson is about the system of real numbers. There are two big categories of real numbers called rational and irrational. We're going to answer some questions about these groups. The Venn diagram that is your foldable that you put in your composition books will really help you to understand these questions if you want to get them out and look at them while you're filling out your example sheet. This says, does the set of whole numbers contain its additive inverse? Well, when we add a number to its opposite, we always get 0. So we cannot add a positive number to a negative number and call them both whole numbers because the whole numbers only include the positives. So the answer to that would be no. Number 2, does the set of integers contain its additive inverses? This would be correct because 5 and -5 are additive inverses. They add up to be 0. 6 and -6 in the integers are all the positive numbers and their opposites. Number 3, does the set of integers contain its multiplicative inverses? A multiplicative inverse is its reciprocal. For instance, 5 and 1/5 would be multiplicative inverses that multiplies to get 1. Well, multiplicative inverses, since 5 and 1/5 are multiplicative inverses, and 2/5 and 5/2, 7 and 1/7, well, there are no fraction integers, so the set of integers does not contain the multiplicative inverses. Or all of them do not, I should say. Number 4, why doesn't 0 have a multiplicative inverse? I bet you can remember that about little Susie, because we cannot have 0 in the bottom of a fraction. If we have 0/1 and we try to flip it over to its reciprocal, that would make it be 1/0, and we cannot divide by 0 or have it in the bottom of a fraction. All right, let's practice classifying the following numbers as rational or irrational. 0, of course, would be a rational number because it's in the set of whole numbers, and so that is rational. 3.2 is also rational. It's can be a mixed number or a whole number with a decimal part. That's an irrational number. Pi is considered irrational number because it is a decimal that never stops and never repeats itself. That's irrational. All right. 1.12 is rational. We learned how to change repeating decimals into a fraction, and a rational number is anything that we can change into a fraction. So we know that's true. Okay. Now, this number may look like it repeats, but if you look carefully, it doesn't repeat. It may have sort of a pattern, but not really, but it doesn't repeat, so it's considered irrational. Now it's kind of tough. We're not going to really talk about numbers like that too much. Now, the square root of any number that's not what we call a perfect square is called irrational. 3 is not a perfect square because nothing can multiply times itself to get 3. So we call 3, since it's not a perfect square number, then the square root of 3 is irrational. The square root of 4 would be a rational number because the square root of 4 is equal to 2, because we know 2 times 2 is 4. So the square root of a number that's a perfect square number, like 4, where it has something that multiplies times itself to get that, the square root of that would be a rational number. Now let's do some true or false. Okay. Number 6, the additive inverse of an irrational number is irrational. Well, that's obviously true. If you thought of pi plus negative pi, that would be equal to 0. You just make a positive and a negative. It doesn't matter that it's irrational. The additive inverse of it's also irrational because one's negative and one's positive. The fact that it's positive and negative is not what makes it irrational. What makes it irrational if it's the square root of a non-perfect square, or if it's a decimal that doesn't repeat and never stops. Okay? Or pi. Pi is irrational. Number 7, the multiplicative inverse of a rational number is irrational. Well, if you think of a rational number like 5, the multiplicative inverse is 1/5. Or, for instance, 2/5, the multiplicative inverse is 5/2. Well, that doesn't make it irrational just to flip over the fraction. Excuse me. Number 8, every integer is a natural number. That's false because negative numbers are not natural numbers. Okay, natural numbers are the counting numbers and they're all positive. All right, let's look at some different examples here. We're going to review some of our properties, and these properties are going to be on our midterm exam in December, so it's good to review. Number 9, we see 3 plus pi equals pi plus 3. We're showing that the order that we add things in doesn't matter. We still get the same sum. So that would be the commutative property of addition. Number 10, we show 4 times 5 minus pi is 20 minus pi. That's our distributive property. That's also going to be on our midterm test, the distributive property, where we have to actually use the distributive property. All right. Hopefully you can remember these examples. If you have to stop and pause this to write down what I've written here, go ahead and do that. I'll kind of scroll up, but we're finished with it. If you've had time to copy everything, you can stop this and begin work on your classwork. Otherwise, I'm going to give you about 1 more minute maybe to copy this.